Hi, my name is Douglas Luke, working with Dr. Patricia Meisner, and my study is designing biodegradable chitosan blends and copolymers for sustainable applications. So why study biodegradable polymers? They decrease plastic waste, break down naturally, they limit microplastic formation, are safer for the environment and all living beings, and are a more sustainable material over time. But why does this all matter? Currently, plastics take hundreds of years to degrade, contributing to lots of pollution and microplastic formation. However, chitosan is a promising biodegradable polymer, naturally occurring in crustacean shells, but it is not yet known how well it blends or copolymerizes with other biodegradable plastics. The research question I've been pursuing is what is the most effective chitosan-based blend or copolymer to limit microplastic presence. And my goal is to analyze blends of chitosan and variable biodegradable polymers to create improved sustainable materials. Here's a list of biodegradable polymers I've been working with, such as chitosan, a linear polysaccharide with hydroxymethyl and amino groups as seen in the top right, as well as biodegradable polyesters, PBAT, PBS, PBT, PHA, and PHB. I've used the Schrodinger material science program to model theoretical copolymerization between chitosan and biodegradable polymers, and have analyzed molecular conformations such as cis and trans, and molecular interactions such as hydrogen bonding and steric repulsion, as well as the compatibility between chitosan and other monomers at the molecular level. I determined which molecular combinations of chitosan and biodegradable polymer are most stable, and I will prepare various blends of chitosan and biodegradable polymers for analysis. Here's a look at my results using the Schrodinger program. Polychitosan forms hydrogen bonds with itself in both cis and trans conformations, as seen on the top. Polychitosan BAT in the trans conformation is strongest due to the intermolecular forces, as seen in the middle left. And polychitosan BS has strong intermolecular interactions, as seen in the bottom left, but also steric hindrance between the functional groups of monomers, as seen in the bottom right. Polychitosan BT has strong attractive forces between all atoms, as seen in the top left. However, the top right shows steric hindrance between all atoms. In polychitosan HA, in both the cis and trans conformations, there is a high presence of strong intermolecular interactions. And in polychitosan HB in the trans conformation, there was an ideal intermolecular forces in the bottom left as seen. However, the bottom right shows strong steric hindrance and repulsive forces. The use of Schrodinger material science allowed for theoretical analysis of copolymerization reactions between both chitosan and various biodegradable polymers. Currently, blends of various composition ratios of chitosan with PBS, PHA, or PBAT are being studied to determine the best composition and ratio. These simulations help predict molecular compatibility, which can inform real-world blending and material design.